Okay, hello class. This is going to be the first lecture of the year. And we're going to talk about work and energy. So what we're going to do today is continue. Let me find my pen. Let's go. No, I like the blue. Set my tablet up. So there we go. So we're looking at work. And we're also looking at energy. We've got to figure out what is work and energy. And energy is either movement or the potential of having to do energy. And usually we talk about energy as potential to do work. And then the question is, what's work? Now here's the thing, with all these different types, they're all kind of bundled together. You know, energy is work, work is energy. We'll come back to that next lecture. But we're going to separate this a bit. What is work? Other than actually doing something. You know, we work with our brains, we work with our hands, we work with our feet. It is an action type of verb, or action word. We actually have to do something. And energy is a bit more ambiguous. We have energy, we have stored energy, we run, we have kinetic energy, we have mechanical energy when something mechanical is doing something, moving, which is work. So what we're going to do is add some technical definitions to this to make it easier for the problems that we're going to work with. And that's what we're going to do today. The first is work. Definition of work is a force moving an object a distance. And so that when we look at this, note that the applied force must be in the same direction as the displacement. So when we're looking at work, the amount of work that's done is force times distance, which is a little bit different than impulse, which we get to later. So work is equal to force pushing something a distance. Multiply those two together, we'll have work. Now, with this definition, work is going to be that force is in the same direction as the distance. So this force that we're working with, this F, it has to be in the same direction as distance. Now here's the thing, is that all of us know that we pull something at an angle, we're actually producing work, but that work is now minimized due to the fact that it's no longer in the same direction as the force, the distance that it moves. And we'll look at that in a minute. And in fact, that when we have an angle, so if we're pushing this way and we're pulling this way, well, you need to know what the force, if this is the total force, we need to know what this force is. And that's just cosine of theta, because here's my angle. So we need to have the force, the amount of force is in the same direction as the direction. So the stuff in the y direction is wasted energy, wasted work, wasted force, because it's not moving that way. We're going to get more complicated later, but this is just the idea what I want you to get at for this part of the chapter, is that work has the force that we're looking for, work that affects the work, has to be in the same direction as D. If not, we've got to use a little bit of trig to figure out what that amount is. So with this example problem, how much work is done on a vacuum cleaner? Pull 3 meters. Oh, we have a distance. So here's our D. In a horizontal direction, by a force of 50 in a direction 30 degrees above horizontal. So I got 50 degrees up. God, this looks bad. But to get the idea, here's my right angle. We want to know what this is. This is X. We want to know the amount of force in this, and this is actually 30 degrees. So the force is actually the hypotenuse times cosine of 30. So, or we can just say the work that's being done is the distance, which is 3 meters. It has to be in meters, times 50 times the cosine of 30. and together that produces the work. And I have my calculator buried on my desk. Here we go. So 50 times cosine of 30 gives me 43.3 times 3. And the work is 129.9, let's say 130 joules. Yeah, and this is one thing we will point out. The unit is in joules because this is going to be kilogram times meters per second squared times meter. So a kilogram meter squared over second squared is equal to joules, which is the same thing as saying mass times velocity squared, which is the same thing as energy. So we'll talk about that later. So when we look at this slide, if we're pushing from the top, let's draw a horizontal. We're looking at this right here. This is going to be 30 degrees from the horizontal. So this amount is 50. We'll still get the same amount of work, which is 130 joules. So a work going this way is 130 joules. But it doesn't matter if we're pushing from the top or the bottom. We're still going to get 130 joules. Now, so here's our equation that we're looking at. Here's the thing. Give you a little bit of hint. Which one's going to be easier to move? This one, where we're pushing up, or this one, when we're pushing down and over? Up and over, or down and over? And you guys are probably going, Dr. Bailey, stop that, you're making me sick. This Y value is actually doing something. We're either reducing the amount of friction by kind of pushing up at the same time, or if we're going this way in the downwards direction and over, we're adding a bit more friction to it. So how we do that's adding a little bit more making it a little bit more complex. Now signs do matter. So when the movement is positive and the force is in the same direction, the work is positive. Excuse me. Work is negative if the displacement of force in an opposite direction. So we're slowing something down. We're actually producing negative work. Constant motion, apply a force in the opposite direction, it slows it down. The work is actually being performed as negative. It doesn't, here's the thing. So let me look at this. So I got something going 50 meters per second in this direction. I apply a force and it slows down to 50 meters per second in over 10 meters. The force that's being applied times 10 is equal to the work. Since it's in the opposite direction of motion, it is then negative. And that is the key, is what are you looking at? What is your perspective on this? And it's a lot easier than it sounds. All right, the example problem. We've got a worker who pushes a crate, which has a normal force of 1,500 newtons. A force of 350, and it travels 24 meters. Assume a coefficient of friction is 0.22. So let's go ahead and draw this. I think I have it here. Normal force is, 1,500 newtons. Friction, the coefficient of friction is 0.220. So we want to know what the net force is, and we need to know the work being performed by friction, the man, and what else? And the worker on the crate, the floor, work done by the floor on the crate. So let's look at friction. Mu, which is equal to 0.220, is equal to friction divided by normal force, which is 1,500. So 0.220 times 1,500 gives me my friction force, and that force is going to be 330. So 330 newtons is my frictional force. So friction is 330 newtons. My net force is going to be 20 newtons. Now, the work being done by friction, which is the floor on the box, okay, the distance is 24 meters. So work is equal to distance, 24 times 330. And remember, this is negative because it's going the opposite direction. And it's negative 7,920 joules. Work done by the man is going to be 350 times 24. Which is going to be 8,400 joules. Now the net work, which is the box going this way, that the box sees, is going to be 20 times 24 in the positive direction, which is 480 joules. And that's going to be the same as 8,400 minus 7,920. That's how everything works out. So this is what we're looking at. This is how you do this problem. A little bit messy, but you get the idea. This is the work of floor on box. This is the man on box. And the net work, which is the sum of all this. If you have any questions, let me know. Thank you, guys.